Okay, last time around we worked with an application. This time we're going to get a little bit more abstract. And we're going to define something that's called a vector space. Okay, so a vector space is a set and an addition operator. Okay, and we're going to make this such that if I have a vector u, v, and w in that set, and C and D are elements of the reals, then the following 10 things have to be true in order to have a vector space. One is that if I add two of these vectors, they still have to be in that set. So this is what we call a property of closure. Okay, that we're closed under addition. You add two things and you stay in there. Okay, so if I commute under addition, it's still going to hold. So I'm going to have a commutative property. If I associate under addition, it's going to hold. So we get an associative property. Number 4, there has to be a 0 vector. So 0 is in the vector space, and what does the 0 vector do? Well, that if I take any vector u in that space and I add the 0 vector to it, I get the u vector back. Okay. Number 5, for every vector u in this space, there exists a vector negative u in that space, such that if I take u plus negative u, I get back the 0 vector. Number 6, I'm closed under scalar multiplication. So if I take a scalar times u, I'm still in the vector space. So that's another closure property. Number 7, I get distribution scalar to vector. So is cu plus cv. That's a distributive property. Number 8, I get a distribution vector to scalar. So this will still hold. That's also a distributive property. Number 9, I get an association under scalar multiplication. So that's an associative property. And finally, number 10, there exists a 1. And 1 times a vector is that vector. So there is a scalar multiplicative identity. So this is a lot of properties that you would have to prove in order to prove that something is a vector space. Now, what is a common list of vector spaces? Things for which these properties hold. Okay, so the big vector spaces that we're going to use in this course are vectors with a finite number under the normal sense of addition. N by n matrices form a vector space. Polynomials of degree n under addition form a vector space. And continuous functions over the interval AB form a vector space. And that interval doesn't necessarily have to be closed. It can also be the interval the all real numbers. Continuous functions over all real numbers also form a vector space, and we'll get into some of that a little bit later on. But once you have like a main vector space, you don't have to go through all of that proving if I can find a vector space that's within a main vector space. So let's take a look at that. So we're going to define something called a vector subspace. Okay. So this is like a smaller vector space. So let's say that I have a vector space. V under plus is a vector space, right? And W is a subset of V. Okay. And if this holds that W, such that W is a vector space, then we call W under addition a vector subspace. Now, we get a neat little theorem here that says something kind of important. The theorem says that if I have a vector space, V plus is a vector space, and W is a subset of V, such that if U and V are in W and C is a real, and U plus V is in W, and C times U is in W. So W is closed under addition and scalar multiplication, right? Then, so it's such that this, if and only if W is a vector subspace. So if W, now it's a minor detail, W cannot be empty. W cannot be the empty set. So there has to be at least one element in W, and namely that element must start with the zero element. Aha. So that's kind of interesting, but that makes sense because that gets, like, if I'm closed under addition or scalar multiplication, zero has to be in there, because like U plus negative U is going to get me 0, and 0 times U will get me 0. Okay, so anyway, what we're saying here is that once that I know that W is a subset of a vector space, and if I can show that W is closed under addition and scalar multiplication, then the other 8 properties of being in a vector space come along. So let's give an example of something that is a vector subspace and then something that is not a vector subspace. Okay, so an example. If I look and make W equal to the set of 2 by 2 matrices that are symmetric. So what is a symmetric matrix? This means that if A is an element of W, then A is equal to its transpose. That's how I get a symmetric matrix, right? Okay, so if I transpose the matrix and it doesn't change, we call the matrix symmetric. So let's try this. We want to know if I let A and B be elements of W and scalar C be an element of the reals, then let's take a look. If I add A to B, right? Well, let's see. The big question is that if I do that, then is it still symmetric? So what we got to check is its transpose, right? So A plus B transpose is the same as A transpose plus B transpose, which is the same as A plus B, which is ultimately the matrix A plus B, which is in W, right? Because if A plus B, right? Because if A and B are in W, then their sum ultimately, let's try this. This is an implication here. That's what it is. That A plus B is in W. How do I know that? Because the transpose is equal to itself through this reaction, which means that the matrix A plus B is symmetric, which means A plus B is in W. So we're closed under addition. That's good. Now I have to show closed under scalar multiplication. All right, so what happens if I take the scalar, right, of A, and I transpose that? Well, that gives me the scalar of A transpose, right, which is equal to C times A, because A is symmetric, which means that, aha, I took the transpose, I got it back, which means that CA is also in W. So I am closed under scalar multiplication. All right, so this implies being closed under addition, and being closed under scalar multiplication implies that the set M of 2 by 2 symmetric matrices is a vector subspace. All right, so that's good news. All right, so let's look at one that is not. Okay, so let's look at a subset that is not a vector subspace. So let's say we're still matrices 2 by 2, but now we're going to let singular, right? So non-invertible, right? So W inverse does not exist. All right, so let A, we're going to disprove that this is a subspace. So let A be 1, 0, 0, 0. Okay, so if I look, the determinant of A is 1, therefore this is clearly in M2 by 2. Sorry, the determinant here is 0. That makes this clearly part of M2 by 2 singular. B, let's make it 0, 0, 0, 1. Also, determinant of 0 makes this a singular matrix. Well, what happens? If I take A plus B, I get the identity. And if you take the inverse of the identity, you get the identity. Identity is not singular. So this means that the set of singular matrices is not closed under addition. If it's not closed under addition, then I do not have a vector subspace. All right, so this is an example of a situation where you can take and disprove vector subspace. So if you get closed under addition and closed under scalar multiplication, then you have a vector subspace. If you lose closure under either one of them, you do not have a vector subspace. All right, so there's your introduction to vectors and vector spaces and vector subspaces. Basically, anything that belongs in a vector space functions mathematically like it's a vector and behaves in the same way. And we will do some more exploring with that throughout this unit. All right, thank you.